Okay, so this is magnetic circuit modeling of a rotary permanent magnet motor. So if we, so I'm just going to review a couple of equations and how we model the permanent magnets. So if you recall that if we have this magnetic equivalent circuit, where this is the length of the magnet and relative permeability goes to infinity, then the magnet is going to create a flux, a field going around flux G, and then there'll be some air gap flux. So from Ampere's law, we have Hm Lm, the magnetic field intensity in the magnet times the length of the magnet, plus Hg Lg is equal to 0. And then we also know if we neglect the fringing because the air gap is small, we could write that Bm Am is equal to Bg Ag, and then where Bm is the magnetic flux density. And then we also know that Bm is equal to mu naught mu r Hm plus Br. So Am is the cross-sectional area of the magnet, and Ag is the air gap area. And so so equation 3 is the equation that governs the magnet material, and we could model it using BH curve, where this crossing point would be here. And so then we also know that in the air gap there is no relative permeability. We just have the permeability of free space. So then from 2 we can rearrange 2. So then we have Bg is equal to Bm Am divided by Ag, and that's 5. And then from 1 we can rearrange 1 in terms of Hm. That will give us minus Hg Lg divided by Lm, or Bg Lg mu naught Lm. That's equation 6. So then we can substitute 5 into 6 to eliminate Bg. So 5 into 6 gives Hm is equal to minus Bm Am Lg divided by mu naught Ag Lm, like that. That's 7. And this gives you the load line. It's more complicated if we don't neglect the relative permeability. If we assume that the relative permeability is finite in the magnetic material. So then this this was the magnet demagnetization characteristic. That's equation 3. And then this one here we can rearrange it to be Bm is equal to minus Hm mu naught Ag Lm over Am Lg, and then that gives the load line that gives the operating point. This will give where the magnet is operating at, and that's important for checking how close it is to the demagnetization and looking at if we are utilizing the magnet material in the most efficient way. So we can carry on and use this model to create a lump parameter model of the magnet. So in order to do that, we can then have a few more steps. Seven, yeah. So if we put 7 back into 3, which I just erased, 7 into 3 gave the demagnetization curve. Then Bm is equal to mu naught mu r Hm plus Br. So if we substitute 7 into 3, we get minus mu naught mu r Bm Am Lg divided by mu naught Ag Lm plus Br. We could, if we rearrange, let's just rearrange this. So we could write minus Bm, and then we have an Lg, a mu naught, and Ag. So let's take that bit out. So then we have Lg mu naught Ag, like that, and then we can also collect the other terms, mu naught mu r Am over Lm, like that. Now, looking at this, you can see that this is the reluctance of the air gap, and this is the permeance of the magnet, or the inverse reluctance of the magnet. So we can then write minus Bm Rg divided by Rm. Remember, permeance is equal to 1 over the reluctance plus Br. That's equation 8. Any questions? Okay, so then we can rearrange and multiply this through so if we multiply both sides by the area, so if we multiply both sides by the area, and define the magnet flux as Bm. Actually, I'll write that after. So we multiply both sides by the area, we'll get flux m is equal to minus flux m Rm over whoops, this should be the other way. Rg, Rm, yeah, plus flux R, where flux m is equal to Bm times Am, and flux R is Br times Am. Then if we rearrange this, we can write flux m is equal to flux R divided by 1 plus Rg over Rm, or multiplying it, we could write this as Rm flux R divided by Rm plus Rg. Or we could, so what does this look like? This looks like current division, right? When we have two terms. So we could draw up what that looks like. So we would have two terms. We have the magnet reluctance, the air gap reluctance, and then we're saying that the flux m is related to flux R, like this. Right? That's just a current division rule. Another way of writing this in terms of permeance is, so we could, permeance is, so that 1 over the reluctance is the permeance, as I said before, so we could also write this as flux m is equal to 1 over Pm flux R divided by 1 over Pm plus 1 over Pg, or that gives Pg flux R over Pm plus Pg. Okay, now if we if we look at this, I think this looks kind of clear, right? That the flux splits up. But it would be better if we could rearrange this. So if you just think about this, we can take this current source, well, flux source, sorry, and move it like that. Right? Or we could so this splits up, or we could write it as like this. Where this in the dotted line is the model of the magnet. So if we go back, we can see that this is the reluctance for the air gap, and this whole piece here represents the magnet in a magnetic equivalent sense. So what is this telling us? This is the reluctance of the magnet. If we look back at the equation here, this is the permeance of the magnet, 1 over reluctance. So the magnet reluctance is Lm over mu naught mu r Am. So if we have a magnet then this is the area, and then this is the length. If you think about this, then this Rm it's the reluctance term that exists within the magnet. So we are going to create this the flux coming out. There's going to be and then this here is from the source within the magnet, but not all of this flux gets out, because some of it's going to come back through the Rm term, and it's not going to go out into the air gap, right? And the amount that goes through is going to be dependent on the magnet reluctance term. So then this will have has some MMF drop across it, which would be the magnet MMF. So that's Fm is equal to the flux R minus the flux M times the reluctance Rm. So that's flux R minus flux M times Rm. Where this flux R, if we go back, that's Br times the area of the magnet. Okay. Now let's think about an actual motor. So here we have a 2-pole rotor at 12 slot. I think it's 12 slot. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, 12. And so if we think about the field, we could draw what the field lines kind of looked like in an ideal situation. So they would the magnetic field would come up, and then it would go through the back iron, and then circulate back around like so, and then through the core of the rotor, and so we could there'd be another field line, and the field lines should go they should go at right angles to the surface of the steel, because it wants to go as quickly as possible back into the magnetic material. So it would come across like this, and then back around, and then go back down through here like that, something like that. And then let me draw one more. The flux could go straight across like that, and then goes through the magnet, and then back around, something like this. Okay, and so then now, and then it has this example here. It has a radius to the stator surface of R, and it has an air gap of G. So if we want to draw up the magnetic equivalent circuit for this, then the first thing to think about is to identify what the main flux paths are. And so it looks like it's going to be all over the place. And so you can see, now I've only drawn the flux lines on one side here, right? But you can appreciate that it's 2 poles, so the other side would be symmetric, right? And also something to note here is that we could draw a line through the center of the shaft like this, and then you can also see that the top half here is a mirror image of the bottom half, right? And that that's a like a mirror image. So now on this example we only have 2 poles. If we had 4 poles or 8 poles, then the electrical degrees would not be the same as the mechanical, but the same mirror image would apply, but it would just be over a smaller length. It wouldn't be over 180 degrees shown here. It would be over 90 or 45 or so on, depending on the number of pole pairs. So we should identify what the main flux paths are on this, and then try to draw up a magnetic equivalent circuit. And so we have, remember we did this in the lecture before that I went over it. We talked about this Carter coefficient, and so you can see here that clearly the air gap is in no way uniform here. It has significant slotting. There's these slots here. But there's equations that approximate or very well, very good field models that account for different shapes of slotting like this, that we could add and change so that we have a different, we modify the air gap length to account for the effect of the slotting in a magnetic equivalent circuit. So that's the kind of idea we're going to do here. And usually the you know, again, it doesn't take up the, if it's usually have more than 2 poles, and so it doesn't, the field lines don't take up such a large portion of the machine. So we have this magnet here, so then we could represent that using the top one, using the idea of this, I don't know why I drew it so darn small. Let me make it bigger. There, that's the same thing, but just bigger. Well, now I've made it too big. So so we've got this source. So it's a flux source in this example, a flux subscript R, like we just talked about, and then we have the magnet reluctance in parallel with it, Rm, and that's what we talked about just before. And then out of that comes a flux M from the magnet. So this is the model of the magnet, and then it's going to, and so this Rm, and I'll talk about that more. The reluctance of the magnet is, so it's the length of the magnet and the area of the magnet and the relative permeability of the magnet. So instead here it's a curved area, and so this is an approximate model, but you can keep improving it to make it pretty accurate, quite accurate. So so then the flux is going to come out, go through, so come out, and then it's going to go across this air gap and then circulate around. So then we could have a reluctance here, and once again I've got myself into trouble by making it so small. So then the flux comes up, and it would either go left or go right. So the flux is going to split. So the flux going up here is the air gap flux, and so this way half of the flux will go this way, and then half of the flux would go on the other half of the machine through the stator yoke back iron, and then it's going to come back, go back around, and then come back up the other side. Okay. Now it turns out though that because of the symmetry, then we can take this point along here as like an equal potential line. So this is like so in this case, because it's only 2 poles, it goes across 180 degrees. So this you could think of as equal potential line, and so in the magnetic circuit then, that at along this line here.
You're off the screen.
Thanks. Okay, just fits. Along this line here, that would be the equal potential line. So this magnetic circuit diagram here. So we've got the magnet reluctance and the air gap reluctance. This has a mirror image across this line that represents the other half of the machine. Okay, and so but we also have one other thing going on here, and so not all of the flux, right, is going to go across the air gap. There's going to be some flux that doesn't comes out of the magnet, but doesn't go through the across the air gap completely. So that's going to be leakage. So there's going to the naughty flux comes out and then skips and doesn't interact with the windings, and so that would be leakage flux. So that's that can be represented by a parallel term where rather than the flux going up through the air gap reluctance, it comes across here and goes back down like so. I'll make a quick drawing of. I'm going to make another. I'll make another drawing of this on the board. So that's the leakage flux. Okay, I think that's so the lower half is a mirror image of the upper half. The way I keep going on about this is because that allows us to actually only solve the magnetic equivalent circuit for half of this because of the symmetry. Then if we solve based on the assuming this point is symmetric, then we can solve. We can use this as an equal potential line because everything would be a mirror opposite. So we can reduce our problem by half. So we only have to model the magnetic equivalent circuit for one pole, and then we can get out the we can get out the proper understanding of how the machine works. So that's a really useful thing, and that's possible because of the symmetry. If it wasn't symmetric, then we couldn't make that assumption. Okay? Any questions? Okay, let me now. So with that, let me now write some equations. So this approach that I'm going over here is based on one pole, and you could use a similar approach to model a induction machine or other types of machines. You just have to think about the flow of the flux for one pole, and then figure out what each of the reluctance terms would be, and that allows you to then create a reluctance equivalent circuit model. So this is quite a general approach, even though it's on a specific machine.